Okay, and so in this video we're talking about how we're going to perform like the write-up, the last conclusion and discussion evaluation of your investigation. And we're going to consider two aspects: the limitations of the experiment itself, which is when you carry out the experiment, when you measure all your results, and if there's any problems that were affecting how well you could do that, and so it's the limitations of the experiment and the limitations of the experimental model. So we're going to use the pendulum as an example. Okay, so pendulum is a good example. Pendulum. There we go. Okay, small interruption. Anyway, we're using a pendulum for an example, and the idea is that in class we set up a really simple system of a pendulum, and we might be modelling a real life situation. That's what we're getting at here. How well does, say, we have a sample that we do where it's a lamp, like a I don't know how you draw a lamp, but it's a lamp hanging from a rope, which is hanging from a tree branch. This is my tree branch. You can tell because it's got leaves and whatever. Okay, it's a tree branch. You get the idea. So the lamp or lantern is swinging back and forward, and then the students go back to the lab and they want to investigate how this swinging is occurring and whether they can model it with an equation. So that's the limitations of the model. We use the lab setup with the retort stand and a clamp, and we have our pendulum hanging from there and swinging back and forward. Is our retort stand. Okay, so those are the two areas we're going to focus on. Now, one of the most important things and the easiest things you can do is to talk about the equation. Okay, so I'm going to be talking specifically here the limitations of the experiment. If you are given an equation, so for the pendulum it's usually this form: T equals 2 pi square root L over G. Okay, what you want to know is, does that equation accurately represent the data that you recorded? So you've got the theory. Every experiment is comparing theory with what is measured. Okay, what we call empirical evidence, data. Okay, so you come up with an equation that might be, let's just give ourselves a little bit more space. We might have an equation which says T equals 2.0 square root L, and then, just because I want to make us a little bit deeper, plus 0.2. Okay, I don't know where 2's are all coming from, but it doesn't matter. And we want to compare that to our theory equation. So the theory equation comparison here, how do we do that? We need to get both those equations of the same form. So I'm going to rewrite the left-hand side equation in the same form underneath this. So this is going to be T equals 2 pi over square root G. So I've just taken that square root G from the bottom, because this is square root L over square root G, and I've shifted it here by itself. And then that's times square root L. Okay, this is the theory equation underneath. So theory and then real. Okay, let's just try and separate those a little bit. Now, the easiest possible way to compare the two is to look at similar parts and see if they're similar. So T and T is no problem. Square root L and square root L is no problem. But we have this 2.0 and 2 pi over square root G. And on the bottom equation, the theory equation, it's actually plus 0, but we don't write it because you don't need to write plus 0. So we've got that to compare it as well, the 0.2 and the 0. And just so you know what that would look like on the transform graph, my equation would be T plotted against square root L. There would be a straight line with a small intercept, the gradient being 2.0. Okay, 2.0, and the intercept being 0.2. I like that, 2.0, 0.2 symmetry, sort of. Anyway, going back to the comparison, this 2.0 here should be equal to this 2 pi over square root g. If they're equal, that means that we've got a very good model. Okay, I keep getting interrupted. Anyway, I was just saying that we want to know if this equation, if the gradients are both the same, the predicted gradient here is the same as the gradient we found on our graph with our results and our data recorded in the lab, then that equation is a good model of the reality. This equation here is the model. This is the reality. Okay. Well, I guess this is a equation model of the reality of an actual pendulum swinging back and forth. Okay, hopefully you get that. Now, if you're in year 13, it's doing level 3 physics, there's going to be an additional factor that you can use in your comparison of the gradients, actually, and the intercept. We'll talk about the intercept shortly, but that is going to be, I'll just write those out over here, you would usually have, say, a gradient measured of 2.0 plus or minus something. It might be plus or minus, say, 0.2. I'll stick with these 0.2s. And you're comparing that to versus 2 pi over square root of g. Now let me just run you through this comparison as I would do it. So 2.0 plus or minus 0.2 means it ranges from 1.8 to 2.2. And you have confidence that the data you measured provides a gradient within that range. Okay. Now 2 pi over square root g is equal to 2 times 3.14, 159.265, etc. Divided by the square root of 9.81. So very roughly speaking, in fact let's not do it rough, we'll do a calculation and then I'll get back to you. Calculation done, 2.005, which is fantastic. So that is the equation, the theory, which tells us my data that I've recorded tells me it should be in that range from 1.8 to 2.2, with 2.0 being right in the middle there. And this is bang on. This is basically bang on, because by the time you round this to the same number of significant figures as my experimental data shows, then we're right there. We're bang on there. So 2.0.